Welcome back. I wanted to prove technical lemma, and we've kind of seen something like this on the homework. It's definitely something that feels very reasonable, and I just want to go through a rigorous proof to give us more practice. So it says that suppose we have two sequences, and one converges to A and one converges to B. If it so happens that the A sequence is less than or equal to the B sequence at every point, then I think quite reasonably it's going to be the case that the limit of the smaller sequence is going to be smaller than the limit. Right? And again, these sort of things are always going to start by looking for an idea. And so our idea might be hoping for contradiction. So I think a lot of you, there was a problem like this back when we were talking about sets and I think least upper bounds and things like that. And so hoping for a contradiction, let's assume that B is smaller than A. So we're going to assume that the bigger sequence Bn, we're actually going to assume that the limit is going to be smaller than the limit of the smaller sequence. And our idea, and I'm going to show you in a picture in a moment, you know, if we know this is true, if we're assuming that B is smaller than A, well, after all, at some point, our points Bn are going to be really, really close to this limit B. So imagine points Bn really, really close to B. And now, some points An are going to be really, really, really close to A. And what's going to happen is that being so close to B and being so close to A, it's going to cause for that term Bn to be really close to B. And similarly, at some point, An is going to be really close to A. And then that's going to break this assumption, right, that An always was to the left. So let's see a picture. Let's see what's going on. So here's my sort of Desmos picture I've got here. And I'm assuming now that B is to the left of A. And what I'm going to do is I'm going to say, well, you know, if An is converging to A, then there's got to be some point that's really, really, really close to A. And similarly, you know, there's got to be some point Bn that's really, really, really close to B. And again, now if I zoom out really far, you know, maybe you can't tell these points apart, but if I zoom in, you know, now I see we kind of get this contradiction. So we're going to have now a point Bn to the left of its corresponding point An, and that's going to violate our assumption. Right? So the last thing we need in this idea is to think about, well, how far across is this interval? So this interval from B to A, that whole distance, is going to be A minus B, the big number minus the little number. And if we kind of cut this in half, and that distance is going to be that distance of that interval over 2, so A minus B over 2, and if we choose that to be our epsilon, well then any point Bn that's within epsilon of B is going to be in this left region. It's going to have to be to the left half of this vertical line I've drawn in. And then similarly, any point An that's within epsilon of A is going to have to be on the other side. And so as long as we can get that point An within that distance of epsilon, I think we're going to get that contradiction we were hoping for. So at this point, the proof idea should be kind of clear. Maybe pause the video and go back and rewatch this part if you're not so sure what the idea is. And now we're gonna do it with inequalities and with epsilons. So let's go back to our slides. So yeah, so we're hoping for a contradiction. We're repeating it. Let's assume that B is smaller than A. And where we're going to let that epsilon be is half the distance between the 2 points. So we're going to do A minus B over 2. And one thing to notice is if I start at the right point, A, and I go to the left a distance of epsilon, I wind up right at the midpoint. And similarly, if I start at the left endpoint, B, and I move to the right a distance of epsilon, I'm also going to arrive at that midpoint. So what's going to be crucial for us is that those two numbers are going to be equal. So let's see what comes next. So since our sequence An converges to A and Bn converges to B, there is going to be some point in time, and let's call that capital N, and after that point, we're going to have that the distance between bn and that limit b is going to be smaller than epsilon, and an and a, that distance is going to be smaller than epsilon. And again, I'm going to emphasize that this is going to be true for n past that certain point. Right, this is something we've got a lot of practice with. And now I'm just going to write these out as double inequalities. This is saying nothing else that bn is within a range of epsilon of b, so it's going to be between b minus epsilon and b plus epsilon. The next one is going to be saying that an is within a minus epsilon and a plus epsilon. And what's going on with these two terms in blue in the middle? Well, we just agreed that those numbers were equal, right? So this kind of middle thing here, that's the same number. And so now what I want us to look at this thing I'm highlighting. So now we have bn is smaller than something, and that something is smaller than an. So I think what that means is that we've just shown that bn is actually smaller than an for, again, after this point in time. And that's a contradiction, right? Because we assumed, I guess we didn't assume, but that was what the hypothesis of our lemma was, that an was always less than or equal to bn for all n. So thank you for watching. Please comment, email with any questions you have. As always with these videos, I recommend trying to rewatch them and then pause the video and see if you can supply the next step, or see if you can reproduce the proof on your own. Ultimately, seeing these proofs, hearing people talk through them, that can be a way that can help us come up with our own proofs in situations where we might not have seen that idea before. So thank you so much for watching. I'll see you soon. Bye.